Today will be a lesson on gas stoichiometry, taking into account all of the mole formulas that we have learned in the course. So when we do some gas stoichiometry, it is the same steps that we have learned throughout the course. So the same 3-step method, or if you have a limiting reactant, you can apply those ideas as well. We can use the formulas for molar mass, or if you have learned molar volume, you can apply those formulas as well. If you have not learned about molar volume, that's okay. You don't need to know it in order to do stoichiometry. And the reason is molar volume is limiting in terms that you can only use it if you have STP or SATP conditions. So again, if you've learned about molar volume, great. If you haven't, it doesn't matter because you can always use the ideal gas law at any of these conditions. So let's do one example together. It says that hydrogen gas is produced when sodium metal is added to water. What mass of sodium is needed to produce 20 liters of hydrogen at SATP? So again, because they're mentioning SATP conditions here, you have the option of using the molar volume formula. If you haven't learned it, that's okay. We're still going to use it, but we'll just use ideal gas law instead. So first thing with any stoichiometry is you got to get your reaction down. So we're saying here that sodium metal is added to water. This is our reaction. So we're going to say sodium in the solid state is added to water in the liquid state. And this is a single displacement reaction. So you should look to see, can sodium kick out hydrogen? And it can, otherwise this question wouldn't exist. But remember that with water, water behaves like this, HOH. So sodium is kicking out this hydrogen and it is combining with hydroxide. So you're going to get sodium hydroxide, which will dissolve in water, AQ, plus hydrogen. And on its own, hydrogen is a diatomic. So again, just lots of little things to remember here as we're ending off the course. Write down what you know. So it's saying what mass of sodium is needed. And then they are producing 20 liters of hydrogen. So my volume of hydrogen gas is 20 liters. And it's at SATP. So again, if you knew molar volume, you could write down the molar volume constant right here. But if you don't know it, then just write down the conditions at SATP. So at SATP, the temperature is 25 degrees C, and we're going to add on 273 immediately to get a temperature of 298 Kelvin. We also know at SATP the pressure is 100 kPa. So we're going to write that down as well. And then we'll be able to do some stoichiometry here. Oh, we have to balance our reaction as well. So when we look at this, my hydrogens are not balanced. And so over here, I have 2 hydrogens. So I have an even number. And on the product side, right here, I have 3 hydrogens. So I have an odd number. So we like to even up our numbers. So I'm going to stick a 2 over here in front of sodium hydroxide so that I have now 4 hydrogens. And then I can balance here, put a 2 in front of water, and then I have to balance that sodium atom as well. So what we'll do is we'll go through our 3 steps. Now, if you want, you can stop here and try this yourself and then just skip ahead to the answer. But if you need an overview, just keep watching. So step 1, we have to figure out the moles of hydrogen because that is the only one that we have lots of information for. And again, you can use your molar volume formula here or use your ideal gas law. So if you're going to use ideal gas law, PV equals nRT, and we're going to solve for moles. So to solve for moles, we're going to take PV and divide it by RT. We're going to sub in our values. So pressure is 100 kPa. This is a constant, so we will not use this number in our rounding of significant figures. Volume is 20 liters, 20.0. That is data given to us. So that's the value we'll round our final answer to. R is also a constant, 8.314 kPa over molk. And then temperature is constant as well at 298 Kelvin. So do the math, make sure that you know how to solve for that. You should get a mole value of 0.80724 moles. And then we need to get over now all the way over to sodium. This is not a 1-to-1 ratio, so we're going to set up a mole ratio. So my moles of sodium are unknown. We're going to compare that to this mole value of hydrogen gas and then equate it to the constants. So remember, if sodium's in the numerator, you need the constant coefficient for sodium in the numerator as well. And then we divide by the coefficient of hydrogen. Cross multiply your moles of sodium should equal 1.6145 mole. And then the last step that we need to do is we need to figure out the mass of sodium. So remember, you know 4 mole formulas. And so you have to have them handy and know which one do you need to use. So this is the mass that we need to solve for. So we need to apply, moles equaling mass over molar mass. So we're going to rearrange and we're going to solve for the mass of sodium. And we're going to take moles times its molar mass. So we've got 1.6145 mole. We multiply by the molar mass of sodium, which is 22.99 grams per mole. And then we get a final mass here, rounded to 3 sig figs because of that volume, of 37.1 grams. The next example is, again, just more of the same. So we're taking ammonia now. They're producing ammonia by reacting nitrogen and hydrogen. And it says what volume of ammonia at 450 kPa, 80 degrees C can be obtained from the complete reaction of 7.5 kilograms of hydrogen. So we're going to let you go through and calculate this. I'll set it up for you, and then I'll give you the answer. Here's an example where you cannot use molar volume. So if you knew the molar volume formula, can't use it because those are only good if you are at STP or SATP conditions. And this is not because it doesn't say. And so you have to use the ideal gas law here. So let's write out the reaction. So we've got nitrogen and hydrogen. And again, got to remember these details. Those are both diatomic gases. And so we write out their formulas, and then we're making ammonia, which will also be a gas. That's a 3. And we have to balance this, okay? So nothing equals. So those odd, even numbers of hydrogen, let's even them up on the product side. We're going to throw a 2 down for a total of 6. I'm going to put 3 in front of hydrogen to get 6 of them, and then my nitrogens are now balanced. Write down what you know. So it's saying what volume of ammonia can be obtained. So my volume is my unknown. The pressure is 450 kPa. And the temperature is 80 degrees C. We're going to add on 273 right away. And we're going to get a value of 353 Kelvin. And again, they don't tell you the R value, the gas constant. They assume you know it. So you can write it down if you want or just stick it in the formula. And then what else do we know? Oh, we know that it's 7.5 kilos of hydrogen. Okay, so our mass here is 7.5 kilograms. We do not want that unit because if I have a mass, I'm going to need molar mass off the periodic table. Those units are in grams per mole. So let's convert this. We're going to multiply by 1,000 and let's convert it to grams. So you're going to have to do a mole value here of hydrogen first. You're going to mole ratio over to ammonia, and then you're going to use the ideal gas law in step 3, and you're going to solve for the volume. You should be getting a volume here of 1.6 times 10 to the 4 liters. That's a lot, but makes sense. You're starting with a lot of hydrogen gas. Or if you're like me and I don't love scientific notation, I would have taken that number and I would have divided it by 1,000, and I would have written an answer of 16 kiloliters. Okay, you can use that too. Good luck, give it a try, and then try some questions on your practice sheet as well.